we have something called as escape velocity. See, escape is escape, right? Velocity is to do with your speed and direction, so on and so forth. So escape velocity is a speed you will need to break free from the planet's gravitational chain. So basically, if I want to exit, if I throw something, say I throw something, what will happen? It will fall towards the ground. If I throw a bit more, it might go further and fall towards the ground. But if I throw with enough energy, it might go around the given planet or even go further away. It can take a very big ellipse. But yeah, if we throw it with enough velocity, it can go so far that it will not come back. Even though gravity has a range of infinity, if we throw with enough velocity, it can reach a point in space wherein it will not be under the influence of the gravitational field per se. Okay, so that's your escape velocity, the velocity with which we should throw an object from a given planet so that it will not fall back. Okay, technically, yeah, it's something like that. Once you stop, you should be out of the planet's gravitational pull. Once you stop, as in come to a rest, right? Once you throw something, technically it keeps going, right? So if you are at a particular height, what happens? It will come back, is it not? So basically it will go this way, but I'm just showing. If I throw something up straight, what happens? It comes back. But if I throw with enough force, if it goes and never comes back, that velocity with which we have thrown up straight is your escape velocity. So as a definition, escape velocity is the minimum speed needed to leave a planet's gravitational field forever without further propulsion. So without any propulsion, right? So without any booster and stuff. So it does not have anything. It keeps going. So this is not there, right? This is not, the object keeps going. And it is gone and it will never come back because of gravitational pull. It will not come back. That's your escape velocity. So let's look at the formula and let's derive it as well. So if you want to figure out the escape velocity of a planet whose mass is m and radius is r, this is your formula. Or if you know the acceleration due to gravity of that planet and you know the radius, we have this formula. And now let's derive this. So let's consider a planet. Say this is of radius r and the mass is m. And we have something like this. And we are launching from here. And we're launching from here. We launch it with our velocity. And that velocity is vi. So this has mass of m. And it has to reach very far away so that, as per what I've written over there, what should be the final velocity? It should come to a rest. Okay, so this we can call it as h or something. And from the center, this point will be h plus re. So there are a few assumptions that we make. Starting from Earth or the planet is spherical of radius r with a center O. M as its mass. Now, let's so derivation, or this comes under assumption only, I guess. Let's consider an object of mass m at a distance x from the center O. Right? The gravitational force at a random point P x units away is f of x is equal to g m by r square. This you guys know, right? Now, the small work done. So we'll start off one thing at a time. See, we have to figure out the velocity. So how do you figure out the velocity? First, we can figure out the energy and then look into kinetic energy, and from there we can figure out the velocity. So to figure out the energy that is needed for this particular task, what we can use is work. So that's what we're doing. So the small work done in moving this object through a small distance dx against the gravitational field is given by, so dw is equal to f dx, which will be equal to g m by r square. All of this we have already done actually. So in this case, sorry, x square. My bad, this is x square. Dx. Right? Next. The total work done in moving the body from the surface of the planet to, so in this case, x will be equal to r, right? To a region see, that's the whole agenda. Beyond that, that's the definition. Influence of Earth's gravitational field. Okay. Where is this point wherein we don't have the gravitational field kind of stops? The furthest point that we can think of, infinity. And so we have the total work done will be equal to integration from r to infinity. And so this will be integration of r to infinity g m by x square dx. So g capital M small m minus 1 by x r to infinity. And as and when we do this, we'll end up with GMM, that will be a positive value, right? So this is the work done. So now with this expression, I can relate it to the velocity. Let VE be the escape velocity. See, quite simple, right? The same funda we have been using with lot of concept before also. Same thing here as well. We're making use of energy to figure out your value of or expression for your velocity at t is equal to 0, right? So kinetic energy at t is equal to 0 is given by half m ve square. This is the velocity which we launched with. So instead of writing vi, let me write it as ve. So obviously we can equate this kinetic energy will be sufficient to place the object at infinity. That's the whole definition. So therefore half mv square should be equal to the work that we already calculated. And so m and m will get cancelled. And we have VE is equal to root of GM2 by R. Root. So if we substitute GM is equal to GR square, if I substitute it over here, we have VE is equal to GR to GR root. And that's your second expression. That's it. Very simple. Right, yes. So this similar derivation, we have done it before also when we are dealing with, when we defined gravitational potential, energy and all of those. Is it not? So I think you can start off with this.